Today we're going to look at the Anova hypothesis test. The generic hypothesis test is for the null hypothesis. We have the mean of the first group is equal to the mean of the second group, equal to the mean of the third group, and so on for however many groups we have. For the alternative hypothesis, we are going to say at least one of the groups has a different mean. I want you to note, this test will not tell us which mean differs, but just that at least one of the means does differ. There's another test called the Tucky test that can tell us which mean or means differ, however. In our class, we will not go over the Tucky test. That is something that we do not get to cover this semester. So why is it called the analysis of variance when the hypotheses are about the means? In ANOVA, it is assumed that each of the populations is normally distributed with the same variance. It turns out that we will determine whether all the means are equal by examining the two estimates of the variance. Again, we're assuming the variance of the first group is equal to the variance of the second group, and that's equal to the variance of the third group, and for however many groups we have. So we're assuming that each of the variances are the same for each of the groups. The test statistic for the ANOVA is the F statistic. It's going to be equal to the variance between the samples, so between each group, and divide that over the variance within the samples, so the difference within just one group. In general, the Anova test is always done on a computer. Statisticians never do these calculations by hand. The first estimate of the variance is called the variance between samples, or the variance due to treatment, and is based upon the sample means. This will only be an unbiased estimator of the variance if the null hypothesis is true. When I say between the samples, let's consider group A, coffee, group B, which is water, and group C is milk. If I want to calculate is there a difference between the reaction times between each drink, then I can compare coffee with that of water and milk. So we're comparing group A, B, and C with each other. That's what we mean by between the samples. Here it looks like the average for the reaction time of coffee is a lot faster than the reaction time for both water or milk. The second estimator of the variance is called the variance within samples, or the variation due to error. This estimate for the variance is independent of the sample means. It will always be an unbiased estimator of the variance. Now here I have the same groups A, B, and C with the same data values. The idea here is I want to look inside the group, and we have 4 different individuals for each group, and we're looking at the variation within one group. Here is the Anova table. Notice that here is the Anova table. The Anova table has 2 sources of variation, the variation of treatment and the variation of error. For the treatment, we're looking at different treatments, such as giving individuals coffee, milk, or water. And the error is the difference between each person within their category. The F statistic is calculated by taking the mean squares of the treatment divided by the mean squares of the error. And the p-value is going to be given here in this box. So all we need to do is know how to read where is our F statistic from the table and where is our p-value. These are the actual formulas for calculating the items in the Anova table. And if you want to pause the video, take a look at these formulas, you can. They are also available on your notes, but I'm going to do everything on StatCrunch, so we really don't need to use any of these formulas for today. We have conditions. Condition number 1. Since we are assuming the population variances are equal, the largest sample standard deviation must be no more than twice the smallest sample standard deviation to perform the test. I'm going to take the smallest sample standard deviation and I'm going to double it. And if I double that number is supposed to be larger than all of the other standard deviations, then the condition is met for the first one. Condition 2. Populations are normally distributed. For that, we'll use the QQ plot and the box plot. Condition 3. The K samples are independent. They cannot be related to one another. Example 1. A researcher organization tested microwave ovens to determine how wattage affected the price of the oven. At alpha equals 0.05, is there a difference in the average price of the three types of ovens tested? Now here you notice that there are three groups. Group 1, Group 2, and Group 3. Since there's three groups, I know this must be an Anova test. There is only one hypothesis test where there's more than two groups, and that's the Anova. Before we start the problem, we'll check the conditions and make sure everything is satisfied before we start the problem. To check our conditions, I will go to Graph and make sure there are no outliers. So we'll go to Graph, Box Plot. We'll highlight all three ovens, and then I want to draw my box plots horizontally. So select Draw Box Plots Horizontally, and we'll press Compute, and here we have the box plot for each of the different types of ovens, and there doesn't appear to be any outliers. I also have to check the condition that each of the populations are approximately normal. So we'll go to Graph and scroll down to QQ plot. I want to highlight all three different types of ovens. And we're just going to press Compute. And we have the QQ plot for the 1000 watt ovens. And I could scroll to the right to look at the 900 watt ovens. And finally the 800 watt ovens, and all three graphs look approximately linear. So since all three graphs look approximately linear, we can assume that the populations are normal. Since all of the conditions are satisfied, we can start step 1. For the null hypothesis, we'll say the mean of the first group is equal to the mean of the second group, and that's equal to the mean of the third group. The null hypothesis is just saying all of the ovens have the same average price. For the alternative hypothesis, we'll just have to write at least one group has a different mean price. Now we're not saying which one is different, we're just saying at least one of the groups has a different mean price. For step 2, we'll just have to state alpha. Alpha in this case is 0.05. Step 3 and 4, we'll go to StatCrunch for those values. We will go to Stat, Anova, and go to One Way, and I want to highlight the 1000 watts, 900 watts, and 800 watts for the columns. And then just press Compute. This will give us the Anova Table, and inside the Anova Table we have the F statistic, which is 10.118, and our p-value is equal to 0.001. For our F statistic, we have that's equal to 10.118, and our p-value is equal to 0.001. Step 5, we're going to ask, is the p-value less than alpha? It is. So we do reject the null hypothesis. there is enough evidence to conclude and our conclusion is always in terms of HA, at least one mean price for a type of oven is different. Since the p-value is less than alpha, we do reject the null hypothesis. There is enough evidence to conclude at least one mean price for a type of oven is different. Example 2. A stock analysis wondered whether the mean rate of return of financial, energy, and utility stocks differed over the past 5 years. He obtains a random sample of 8 companies from each of the 3 sectors and obtains the 5-year rate of return in percent. Are the mean rates of return different at alpha equals 0.05 level significance? We are talking about 3 different groups, financial, energy, and utilities, so I know again that this must be an Anova test, since we're talking about 3 different groups. In this example, we are given the StatCrunch output for the problem already. We just need to make sure all of the conditions are met. If I look at the standard deviation of the smallest value, we know that the standard deviation of the smallest value is 4.5, and if I double it, it's clearly larger than all of the other values, so the condition is met for the standard deviation. We could look at the box plot also, and the box plot indicates that there are no outliers, so that part of the condition is also met. The QQ plot for the financial sector looks approximately linear. The QQ plot for the energy sector looks linear as well. And that also includes the utility sector. So all of the conditions are met. We can try the problem. Step 1, we're going to state the null hypothesis. And I'm just going to say the mean of the first group is equal to the mean of the second group, and that's equal to the mean of the third group. For the alternative hypothesis, we're going to write at least one group has a different mean rate of return. In step 2, we'll just state alpha. Alpha is 0.05. In step 3 and 4, we'll go to StatCrunch to find our values. We have the f-stat is equal to 2.077, and our p-value is equal to 0.15. Now in step 5, we're going to ask the same question like always. Is the p-value less than alpha? Is 0.15 less than 0.05? In step 5, the p-value is not less than alpha, so we do not reject the null hypothesis. There is not enough evidence to conclude at least one sector has a different mean rate of return. Since the p-value is not less than alpha, we do not reject the null hypothesis. There is not enough evidence to conclude at least one of the sectors has a different mean rate of return.